The purpose of this video is to show the difference between constant and variable rates of change. Got a bit of text here to highlight a relationship which has a constant rate of change, means that the average rate of change between any 2 points on the curve are equal. Okay, let's see if we can highlight that. Okay, let's have a go at trying to apply that definition to this graph here. So what that's saying is that this relationship that we have has a constant rate of change if the average rate of change from A to B is the same as the average rate of change from B to C. Okay, basically, if this rise over run is the same as this rise over run. So let's have a go at doing this. We've got y's and x's, so I'll call this point to 80, I'll call this x1, y1. And this other point for 160, call you x2, y2. So the difference between the y's on the difference between the x's will give me 40. I'll do the same thing in another color between B and C. Okay, so for 160, my 2 points, for 160, which I'll call x1, y1, and 6 to 40, which I'll call x2, y2. Average rate of change is the difference between these 2 points. 240 minus 160, 16 minus 4. Okay, I'm going to get 40, and then I can write some conclusion saying that since the average rate of change of AB is the same as the average rate of change of BC, okay, there is a constant rate of change from A to C. Okay, once we're satisfied that there's a constant rate of change, we can use that idea to find relationships between variables. So we've done this before in a straight line with y equals mx plus c. Okay, essentially the gradient is going to be the average rate of change between any 2 points. Okay, hopefully you realize some similarities between average rate of change formula and gradient formula. Remember, it's just exactly the same thing. Since we've got v and t, instead of using y equals mx plus c, we're going to use v equals mt plus c. Okay, this is my y and this is my x, but we need to get away from leaning on those letters so much. Okay, I know that the vertical axis intercept, okay, normally called the y-axis intercept, is 0, 50, which implies that my c value is 50. Looking at the average rate of change, I'm looking at the change in volume on change in time. So V2 minus V1 on T2 minus T1. Label this point 0, 50, T1, V1. And I'll label this point 30 to 60, which will be T2, V2. Substituted in all these values. Okay, I get something like 210 on 30, which equals 7 liters per minute. So my function, which was v equals mt plus c, okay, the relationship between the two variables will be v equals 7. This is 7t plus 50. Okay, so we can use y equals mx plus c when we know we've got a constant rate of change. In some scenarios, we won't have constant rates of change. We'll have variable rates of change, where the average rate of change between 2 points can vary over the domain of the function. We've done these sort of calculations before. So remember, we went from 1 to, we went from 0 to 1 second and looked at the slope of this line, and then looked at, say, the last second of flight. Okay, clearly we can see that between A and B and C and D, the average rates of change are different. Okay, that they can vary, they can change. So we'll note average rate of change of AB isn't the same as the average rate of change of CD. So there is a variable rate of change from A to D. Okay, variable meaning not constant. For some of these non-constant or variable rates of change, we'll be able to draw graphs to show how the rate of change varies over time. Okay, so looking at this scenario, we've got water being poured steadily into each of these vessels. Okay, imagining that a tap is being opened and water is just flowing in here. Draw a graph that shows the relationship between the height of water and the volume that's being poured in. So all of these graphs will be HV graphs. Pouring water into this sort of a vessel, okay, would know that the water level would increase at a constant rate. Okay, hopefully we've seen this filling up our water bottle at the taps, and then hopefully we don't see this too often, where it gets to the really narrow part of our bottle and just explodes through. So the way that we would see this is, as I'm pouring in volume, it would go up at a constant rate, go up at a constant rate until it gets to this narrow part at the top, after which the rate would rapidly increase. Okay, so constant, nice slow rate, and then rapidly increase. And about here is where you normally get wet and cranky. Okay, looking at the next one, we're going to have a similar sort of scenario. Okay, it's wide at the bottom and then gradually gets narrower as we go up the vessel. So it's going to start out pretty slow and then gradually get more and more steep. So instead of just drawing these little lines piecewise, the way it'll actually look is something like this. A smooth curve where we can see these slopes are gradually getting steeper as we go up. Okay, part C, again, a bit more interesting. Starts off relatively narrow and then gets wider. Okay, it gets wider to this widest point and then starts getting narrow again. So for this first little section, I might just annotate some of these. So this is 0, this is A, and this is B, and I'll just note these on my graph, 0, A, and B. So here's 0, I'll call this A, and call this B. So from 0 to A, because the vessel's getting wider, the rate of change will get slower. So we'll see something like this happening from 0 to A. Okay, and then from A to B, what we'll see is it's getting narrower, so it'll start to speed up. It's horrible. Okay, so it'll start to speed up. Okay, until it's full at that point. The final one, we've got a few little sections here. So it starts out really wide, gradually gets less wide. Okay, until it reaches some point, and then it becomes wider again. So I'll call this point A. A gets narrower, 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 and wider again, point B, and then narrows again. So what this one will look like is, because it's getting narrower, okay, it'll start speeding up until the point A, and then it's going to get wider again, but it's not going to get as wide as it was before, so it won't be quite as slow, so it might just miss a little bit of this function. Okay, to point B, and then again until we're full up the top. Okay, so I could probably draw this a little bit better. Looks something like that. Okay, where these little points are not smooth. Recommend that you click on this link and play this game, where you need to try and match the shape to this. This is a constant glass, so that one's not it. No, I was thinking that would be okay. Maybe one of these. Maybe this one. Yeah, filling out nice and slow at a constant rate. So you can play that for a bit. And make sure you have a go at these questions.